Hi, this is David Quatello with Siemens. In today's BrainShark video, we'll be discussing the basics of the Siemens panel boards. This course covers the basic power distribution concepts and provides an overview of Siemens panel boards. You should have a basic understanding of electrical concepts to fully benefit from this course. Let's get started. Here are just some of those legal trademarks that we need to cover. Okay, so what are the objectives? Upon completion of this course, you'll be able to define the term panel board, explain the role of panel boards in a distribution system, explain the need for circuit protection, identify 3 types of panel board main configurations, identify various power supply systems, describe important characteristics of panel boards as service entrance equipment, describe the proper grounding techniques of service entrance and downstream panel boards, describe the 5 Siemens P-Series panel board models, identify key ratings of Siemens P-Series panel boards, identify Siemens P-Series panel board options, and finally, identify additional Siemens panel board types. This course has 3 parts plus a final exam. The first part is an introduction that covers basic power distribution concepts. The second part covers panel board concepts. And the third part covers Siemens panel boards and related accessories, and then we will have a final exam. Power distribution systems are used in every residential, commercial, and industrial building to safely control the distribution of electrical power throughout the facility. Most of us are familiar with the power found in the average home. Power, purchased from a utility company, enters the house through a metering device. The power is then distributed by a load center to various branch circuits for lighting, appliances, and electrical outlets. Power distribution systems used in multifamily, commercial, and industrial facilities are often complex, but like a residential load center, they are designed to safely distribute power to devices and systems that perform useful functions. The power provided to a commercial or industrial facility is much greater than that provided to a home. This power must be divided and safely distributed to various devices and systems with specific current and voltage requirements. Where large amounts of power are handled, switchgear and/or switchboards are used. Where more moderate amounts of power are distributed, panel boards are used. Good distribution systems don't just happen. Careful engineering is required to ensure that the distribution system safely and efficiently powers existing loads and has expansion capacity for possible future loads. Electrical distribution systems, whether simple or complex, typically include panel boards. Even the load center used in a home is a type of panel board. However, the focus of this course is on panel boards used in commercial and industrial facilities. A panel board is a type of enclosure for overcurrent protection devices and the buses and connections that provide power to these devices and their associated circuits. According to the National Electric Code, a panel board is used to control light, heat, or power circuits, placed in a cabinet or cutout box, mounted in or against the wall, accessible only from the front. For additional information, refer to Article 408, Switchboards and Panel Boards, in the NEC. Panel boards are frequently divided into 2 categories. First, lighting and appliance branch circuit panel boards, and the other are power panel boards. Prior to the 2008 NEC, the distinction between these 2 panel board types was described in NEC Articles 408.34 and 408.35. These articles placed restrictions on lighting and appliance panel boards and indicated that panel boards that did not comply with these restrictions were defined as power panel boards. For example, a lighting and appliance branch circuit panel board had to have more than 10% of its overcurrent protection devices, that's not including the mains, protecting lighting and appliance branch circuits. A lighting and appliance branch circuit is one with a connection to the panel board neutral and an overcurrent protection device rated for 30 amps or less. For the purpose of this definition, each pole of a device is considered as one device. Additionally, a lighting and appliance panel board was allowed a maximum of 42 overcurrent protection devices, or poles, in any one cabinet or cutout box. Articles 408.34 and 408.35 and their associated restrictions were removed from the NEC, beginning with the 2008 code. However, the terms lighting and appliance panel board, also called the lighting panel, and power panel board, also called a power panel or distribution panel board, are still widely used. Because current flow in a conductor always generates heat, the greater the current flow, the hotter the conductor. Excess heat is damaging to electrical conductors, and for that reason, conductors have a rated continuous current carrying capacity or ampacity. Current beyond the rated capability of a conductor is referred to as overcurrent. Overcurrent can result from a short circuit, overload, or ground fault. A short circuit occurs when two bare conductors touch, causing the resistance between the conductors to drop significantly. This reduction in resistance causes an immediate and destructive increase in current. An overload is typically a much lower current than a short circuit. An overload occurs when too many devices are connected to a circuit or when electrical equipment is made to work beyond its rated capabilities. Finally, a ground fault occurs when current takes an undesired path to ground. The level of ground fault current depends on the resistance of the path and the amount of voltage applied. Overcurrent protection devices are used to protect conductors from excessive current flow. Some overcurrent protection devices only provide protection in the event of a short circuit. Some provide both short circuit and overload protection, and some devices provide protection in the event of any of the three overcurrent types. Circuit protection would be unnecessary if overcurrents could be eliminated. Unfortunately, overcurrents do occur, and when an overcurrent occurs, a protection device must automatically disconnect the electrical equipment from the voltage source. An overcurrent protection device must also be able to recognize the difference between a small overcurrent and a short circuit and respond in the proper way. A small overcurrent is often allowed to continue for a short time, but as the current magnitude increases, the protection device must respond faster. Short circuits must be interrupted immediately. A fuse is a one-shot device. The heat produced by an overcurrent causes the current-carrying element to melt open, disconnecting the load from the source voltage. Non-time delay fuses provide excellent short-circuit protection. When an overcurrent occurs, heat builds up rapidly in the fuse. Non-time delay fuses usually hold 500% of their rating for approximately 1/4 second, after which the current-carrying element melts. This means that these fuses cannot be used in motor circuits, which often have inrush currents greater than 500%. Time delay fuses provide overload and short circuit protection. Time delay fuses usually allow 5 times the rated current for up to 10 seconds to allow motors to start. Underwriters Laboratories, or UL, establishes and standardizes basic performance and physical specifications for products that undergo its safety test procedures. Among the standards developed by UL are standards for classes of low voltage fuses. Those are fuses with voltage ratings of 600 volts or less. The accompanying graphic shows the fuse classes most commonly found in panel boards. Fuses are grouped into classes based on their operating and construction characteristics. Each class has an interrupting rating, which is the maximum current the fuse is capable of safely interrupting. Fuses also have maximum continuous current and maximum voltage ratings. When selecting fuses, it's a good idea to refer to the fuse manufacturer's application data to make sure that a specific fuse is appropriate for the type of loads involved. A fusible disconnect switch is one type of device used in panel boards to provide overcurrent protection and a manual means of controlling power distribution. Fuses located in the switch are selected to handle the specified levels of current and voltage and to provide the appropriate interrupting rating. Siemens vacuum brake fusible switches through 600 amps feature a clamp-matic action that holds the current carrying contact surfaces in a vice-like grip. Heat buildup due to current is minimized. When the switch is moved to the off position, the movable contact snaps from between the jaws, providing a quick, clean break. Twin arcs are produced, which are smaller and extinguish quicker than a single arc produced by other designs. The contacts are surrounded by an enclosed arch chamber which absorbs much of the heat from the arcing. The enclosed chamber limits oxygen to more rapidly cool and extinguish arcs. Siemens high contact pressure (HCP) fusible switches have continuous current ratings from 400 amp to 1200 amp. Another device used for overcurrent protection is a circuit breaker. Although some circuit breakers do incorporate fuses, most do not. But, like a fusible switch, a circuit breaker provides overcurrent protection and a manual means of controlling power distribution. When an overcurrent occurs, the circuit breaker trips to remove power from the circuit. The greater the overcurrent, the more rapidly the circuit breaker trips. Once the overcurrent condition has been corrected, a simple flip of the breaker's operating handle restores the circuit. The ability to restore a circuit without replacing a fuse is one of the key advantages of a circuit breaker. However, circuit breakers have other advantages as well. For example, some circuit breakers have adjustments or a replaceable trip unit to allow the level of fault current required to trip the breaker to be set to match the application. Some circuit breakers also have communication capability to allow information to be sent to power monitoring equipment or display devices. Circuit breakers are rated according to the maximum voltage they can handle. The voltage rating is a function of the circuit breaker's ability to suppress the internal arc that occurs when the circuit breaker's contacts open. The voltage rating of the circuit breaker must be at least equal to the circuit voltage. The voltage rating of a circuit breaker can be higher than the circuit voltage, but never lower. For example, a 480 volt circuit breaker could be used in a 240 volt circuit, but a 240 volt circuit breaker could not be used in a 480 volt circuit. Some circuit breakers have what is referred to as a slash voltage rating, such as a 120/240 volt, or, as shown in the accompanying graphic, 600/347 volt for 2, 3, or 4 pole NEB breakers, and 115/250 VDC for 2 pole NEB breakers. In such cases, the breaker may be applied in a circuit where the nominal voltage between any conductor and ground does not exceed the lower rating, and the nominal voltage between conductors does not exceed the higher rating. Every circuit breaker has a continuous current rating, which is the maximum continuous current a circuit breaker is designed to carry without tripping. The continuous current rating is sometimes referred to as the ampere rating because current is measured in amperes, or more simply, amps. The rated current for a circuit breaker is often represented as IN. This should not be confused with the current setting IR, which applies to those circuit breakers that have a continuous current adjustment. IR is the maximum continuous current that circuit breaker can carry without tripping for the given continuous current setting. IR may be specified in amps or as a percentage of IN. Conductors are rated for how much current they can carry continuously. This is commonly referred to as the conductor's ampacity. In general, the ampere rating of a circuit breaker and the ampacity of the associated conductors must be at least equal to the sum of any non-continuous load current plus 125% of the continuous load current. Siemens circuit breakers are rated on the basis of using 60 degrees Celsius or 75 degrees Celsius conductors. This means that even if a conductor with a higher temperature rating were used, the ampacity of the conductor must be configured on its 60 degrees Celsius or 75 degrees Celsius rating. The circuit breaker frame includes all the various components that make up a circuit breaker except for the trip unit. For any given frame, circuit breakers with a range of current ratings can be manufactured by installing a different trip unit for each rating. The breaker frame size is the highest continuous current rating for a breaker with a given frame. Each circuit breaker has an interrupting rating, also called an ampere interrupting rating, that specifies the maximum current the circuit breaker is designed to interrupt. Because UL and IEC testing specifications are different, separate UL and IEC interrupting ratings are often provided. When designing a power distribution system, a main circuit breaker must be selected that can interrupt the largest potential fault current that can occur in the selected application. The interrupting ratings for branch circuit breakers must also be taken into consideration, but these interrupting ratings will depend upon whether series ratings can be applied. The interrupting rating for a circuit breaker is typically specified in symmetrical RMS amperes for specified rated voltages. RMS stands for root mean square, which refers to the method for calculating an RMS value. The RMS value is also called the effective value of an alternating current or voltage. The term symmetrical indicates that the alternating current value specified is centered around zero and has equal positive and negative half cycles. Siemens circuit breakers have interrupting ratings from 10,000 to 200,000 amps. These and other ratings for Siemens circuit breakers can be found in the SpeedFacts catalog, which is available on the Siemens website. Okay, section 1 is completed, so let's go into our knowledge check. Which of the following descriptions does not agree with the NEC definition of a panel board? Is it A, used to control light or power circuits, B, accessible from the front, C, accessible from the rear, D, mounted in or on a wall, or E, placed in a cabinet or a cutout box? Overcurrent can result from A/and A, short circuit, B, overload, C, a ground fault, or D, all of the above. Question 3. Which of these fuse classes has the lowest interrupting rating? Is it A, H, B, J, C, L, or D, T? Question 4. A circuit breaker frame size is the blank continuous current rating for a given circuit breaker frame. Is it A, lowest, B, average, C, highest? Last question for section 1. Which of the following circuit breaker ratings is the maximum level of current that a circuit breaker is designed to interrupt? Is it A, continuous current rating, B, ampere rating, C, frame size, or D, interrupting rating? Alright, so we just finished part 1 of the Basics of Panelboards. So we're going to move over to part 2. In this part of the Basics of Panelboards, we'll cover panel board concepts. Panel boards are available in different sizes with variations in construction. For simplicity, the accompanying graphic shows the components that make up a can for a typical lighting panel. A can is the part of the panel board enclosure that mounts in a wall, flush mounting, or to a wall, surface mounting. The can is typically constructed of galvanized steel. Removable blank end panels allow the user to cut whatever conduit holes are necessary. Pre-stamped knockouts are available as an option. Mounting studs are used to support the interior or group-mounted devices. The interior consists of several components, including overcurrent protection devices, bus bars, and insulated neutral bus bars. For a lighting panel, the interior is mounted to the 4 mounting studs in the can. Jacking screws, not shown, allow adjustment of the interior within the enclosure. A bus bar is a conductor that serves as a common connection for 2 or more circuits. Standard bus bars on Siemens panel boards are made of aluminum, but copper bus bars are available as an option. NEC Article 408 requires three-phase panelboard bus bars to have phases in sequence as shown in the accompanying graphic so that an installer can have the same fixed phase arrangement in each termination point in a panelboard or switchboard. NEC Article 408 does provide an exception to this rule. Refer to this article for additional details. Some power supply systems use a transformer with a three-phase, 4-wire, delta-connected secondary with a grounded center tap connection on one phase. The accompanying illustration shows an example of such a system with 240-volt phase-to-phase. The midpoint of one phase winding is grounded to provide 120 volts between phase A and a neutral and 120 volts between phase C and neutral. Between phase B and neutral, however, the voltage is 208. This is referred to as the high leg. NEC Article 110.15 requires that the high leg conductor on bus bar be permanently marked with an orange finish, or by other effective means, at a point where the connection is made, if the ground conductor is also present. In addition, NEC Article 408.3e states that the B phase should be the high leg. NEC Article 408.3e does permit some exceptions to this rule for existing installations or metered service equipment. Refer to the article for details. More information on calculating the value of the high leg, as well as connecting loads, is discussed later in the course. Siemens lighting panels feature a split neutral design, which means that neutral connections are available on both sides of the panel board. Split neutrals are connected by means of an insulated neutral bus bar. Some loads can cause harmonics and non-linear loading on a distribution system. This requires special consideration when ordering a panel board. One way to deal with non-linear loads is to double the capacity of the panel board neutral. A 200% neutral is an available option on Siemens panel boards. While it is common for load centers to have plug-in branch circuit breakers used in panel boards for commercial and industrial applications typically bolt onto the bus bars. The accompanying illustration, for example, shows two BL circuit breakers. One is mounted to the panel board bus and the other being mounted. Specifications typically require panel board circuit terminals to be labeled or for a wiring diagram to be provided. One approach for numbering terminals is to use odd numbers for poles on the panel board's right, your left as you face the panel board, and even numbers on the panel board's left. This is sometimes referred to as the NEMA numbering. For some specifications, however, vertical numbering is required. The label provides important warnings and key information about the panel boards, such as the voltage system it is designed for and the ampere rating. The accompanying graphic shows a typical lighting panel. The dead front and trim are the front surfaces of the panel board that cover the interior. The trim includes an access door. These components provide access to the overcurrent devices while sealing off the bus bars and internal wiring from contact. QF3 filler plates are used to cover any unused pole spaces not filled by a circuit breaker. The National Electrical Manufacturers Association, or NEMA, has guidelines for electrical equipment enclosures. Siemens panel boards are supplied as standard in a NEMA Type 1 enclosure intended for general purpose indoor use. The following enclosures are available as an option. Type 3R enclosures are intended for outdoor use primarily to provide a degree of protection against rain, sleet, damage from external ice formation. Type 4X enclosures are intended for indoor or outdoor use primarily to provide a degree of protection against corrosion, windblown dust and rain, splashing water, hose-directed water, and damage from external ice formation. Type 3R-12 enclosures are intended for indoor use primarily to provide a degree of protection against circulating dust, falling dirt, and dripping non-corrosive liquids. panel board installation requires careful planning to ensure a safe environment for personnel and equipment. Article 110.26 of the NEC covers spaces about electrical equipment such as panel boards. The intent of Article 110.26 is to provide access and enough working space for personnel to examine, adjust, service, and maintain energized equipment. Article 110.26 sets requirements for the depth, width, and height of a working space. In addition, Article 110.26 discusses entrance requirements to the working space as well as requirements for dedicated equipment space for indoor and outdoor applications. If you will be involved in planning a power distribution system, you should familiarize yourself with Article 110.26. NEC Article 408.36 requires panel boards to be protected by an overcurrent protection device with a rating that does not exceed the panel board's rating. As shown in the accompanying illustration, the main overcurrent protection device may be an integral part of a panel board or located between the panel board and its power source. In this example, the main breaker and panel board are both rated for 600 amps. NEC Article 408.36 does provide for exceptions to this rule. Refer to the complete article and NEC Article 230.71 for additional details. One of the exceptions to NEC Article 408.36 allows panel boards to be protected by two main circuit breakers or two sets of fuses, provided that the combined current rating of these devices does not exceed the current rating of the panel board. When two main circuit breakers or two sets of main fusible switches are used in a panel board, a split bus is used. Half of the branch circuits are protected by one main device, and the other half are protected by the other main device. Frequently, a panel board is supplied by the secondary of a transformer. When this is the case, according to NEC Article 408.36, overcurrent protection for the panel board must be provided on the secondary side of the transformer. The overcurrent protection device can be installed either ahead of or in the panel board. The NEC Article 408.36 provides an exception to this rule. Refer to this article and NEC Article 240.21 for additional details. There are three types of panel board main configurations: main lug only, main breaker, and main switch. In this context, the term switch refers to a fusible switch. All three of these configurations are available for power panels. Lighting panels are available with either a main lug only or a main breaker configuration. The incoming supply cables of a main breaker type panel board are connected to the line side of the main breaker, which in turn feeds power to the panel board and its branch circuits. The main breaker disconnects power from the panel board and protects the system from short circuits, overloads, and ground faults, if equipped with ground fault protection. Siemens main breakers are bus connected to the main bus bars. This means there are no cable connections required from the main circuit breaker to the lugs on the main bus bars. Bus connecting provides a higher degree of circuit integrity because there is less chance for loose connections, which can lead to overheating. Depending on the panel board, the main breaker can either be mounted horizontally or vertically. A main lug only type panel board does not have a main circuit breaker. The incoming supply cables are connected directly to the bus bars. Primary overload protection for the panel board is not provided as an integral part of the panel board. There are various ways a main breaker and a main lug only panel board might be used in the same application. For example, in the accompanying graphic, the feed-through lugs mounted on the main bus of the main breaker panel board are connected to the main lug-only panel board. The main breaker provides overcurrent protection for both panel boards. Subfeed lugs are mounted directly beside the main incoming lugs on a panel board and are used to connect one or more additional panel boards to the same feeder. In the accompanying graphic, Two adjacent main lug-only panel boards are connected to the feeder through a fusible switch or circuit breaker. Power supplied by the overcurrent protection device is routed to the panel board on the left and through sub-feed lugs to the panel board on the right. Circuit breaker or fusible switch mounting height is sometimes referred to as unit space. The unit space available for mounting branch devices depends on the panel board type, enclosure dimensions, and main device configuration. Because the unit space required by circuit breakers and fusible switches varies, the number of branch devices that can be mounted in a panel also varies. For Siemens panel boards, the unit space available and the unit space required by each device can be found in the SpeedFacts catalog, which is available on the Siemens website. When an application requires a circuit breaker that is larger frame size than the branch circuit breakers available and will not fit in the branch circuit's location, a sub-feed breaker can be used. One possible application is to supply a second panel board located some distance from the first panel board. This is, however, not the only application. A sub-feed breaker can supply any load that a branch circuit breaker can supply. Panel boards receive power from a variety of sources. For example, a downstream panel board typically receives power from an upstream panel board or switchboard. However, power for the distribution system originates from a utility power company. Power from the utility is stepped down through a transformer for distribution to a facility. There are a number of ways that the transformer's secondary windings providing service may be configured. In order to properly select a panel board, you need to understand which voltage and system will be connected. The examples shown in this course are a few of the more common systems, but other systems and voltages are also common. The accompanying diagram illustrates a common single-phase, 3-wire distribution system. As the diagram shows, the voltage between the neutral connection of the transformer secondary and either side of the secondary is 120 volts, and the voltage across the entire secondary winding is 240 volts. The accompanying illustration shows the secondary of a 480-277 3-phase 4-wire Y-connected transformer. The 480Y indicates the transformer is Y-connected and has 480 volts between any two phases. The 277 volt indicates the voltage between any phase and neutral is 277 volts. If you know the phase voltage for a system like this, you can calculate the phase-to-phase voltage by multiplying 1.732 times the phase-to-neutral voltage, which is 277 volt, times 1.732, which equals 480 volts. A 3-phase 4-wire delta-connected secondary works a little differently. The accompanying illustration shows a delta-connected secondary with 240 volt phase-to-phase. The midpoint of one phase winding is grounded to provide 120 volts between phase A or C and the neutral connection. Between phase B and neutral, however, the voltage is 208 volts. As previously discussed, this is referred to as the high leg. 4-wire delta-connected transformers with a high leg are most often wired so that the B phase is the high leg. In such cases, the high leg voltage can be calculated by multiplying the phase A or C to the neutral voltage times 1.732. So in this case, 120 volts times 1.732 equals 208. It's important to note that not all circuit breakers are suitable for use on the high leg. For example, breakers rated for 240-120 volts can be installed on legs rated for 120 volts, but cannot be installed on the high leg, 208 volts. You may remember that NEC Article 110.15 requires that the high leg bus bar or conductor be permanently marked with an orange finish or by other effective means. This will help to avoid someone from connecting a 120 volt single phase load to the 208 volt high leg. Sometimes panel boards are used as service entrance equipment for a building. This is the equipment located near where the power enters the building. The incoming power is connected to this equipment, which provides a means to control and cut off the supply. According to NEC Article 408, panel boards used as service entrance equipment must be approved and labeled as such. Siemens offers panel boards that are factory labeled as suitable for service entrance equipment when NEC requirements are met. It is important to note that the 6 disconnect rule refers to the number of disconnects and not the number of poles. For example, the main lug-only panel board shown in the accompanying illustration has 18 poles but only 6 circuit breakers. 3 poles are mechanically linked together to form one disconnect device. Because the service can be disconnected with no more than 6 operations of the hand, this arrangement meets the 6 disconnect rule. Grounding is an important aspect of any electrical equipment and must be considered carefully. A ground connection is a connection to earth or to a conductive object that is connected to earth. The accompanying illustration, for example, shows the neutral conductor of a Y-connected transformer connected to ground. The intentional grounding of electrical equipment is done to limit voltage differences between parts of the system. This is necessary for the safety of personnel and the protection of equipment and facilities. Article 250 of the NEC covers grounding and bonding requirements for electrical installations. The panel board neutral conductor is grounded only at the service entrance, never at any downstream equipment. In the accompanying illustration, the neutral is grounded at the service equipment by connecting a conductor from the neutral grounding conductor to a grounding electrode. The neutral and the panel board enclosure are bonded together at the service entrance so that the enclosure is also connected to ground through the grounding electrode connector. Bonding permanently joins metal parts to form a low resistance path for electrical current. A panel board may also require an equipment grounding bus, which is non-insulated and mounted inside the panel board directly to the can. All feeder and branch circuit equipment that are connected to the equipment grounding bus are at the same potential as the panel board can. Siemens panel boards come with an equipment grounding bus. As previously discussed, the neutral conductor is only connected to ground at the service entrance. Beyond the service equipment, the neutral is always insulated. When a downstream panel is used, the neutral is insulated in that panel. As shown in the accompanying illustration, the enclosure of the downstream panel is connected to ground through a grounding conductor back to the service entrance equipment. In the accompanying illustration, branch load number 2 has become shorted to its metal enclosure. Fault current is returned to the source through the path indicated. With a properly coordinated system, the branch circuit breaker in the downstream panel board will open, removing the load from the power source. A ground fault is a condition in which electrical current unintentionally flows to ground. Because ground faults can cause damage to equipment and can endanger lives, ground fault protection is required in some situations. For example, NEC Article 230.95 requires ground fault protection of equipment for service disconnects rated 1000 amps or more on solidly grounded Y services exceeding 150 volts to ground but not exceeding 600 volts phase to phase. Refer to the complete article for additional information. Keep in mind that ground fault equipment protection must open a circuit when ground fault current reaches 30 milliamps. In contrast, ground fault circuit interrupters designed to provide life protection must open a circuit at 5 milliamps, plus or minus 1 milliamp. When ground fault protection is incorporated into a panel board, it is generally through the use of circuit breakers with ground fault protection. One way a ground fault protector works is to install a sensor around the insulated neutral bonding jumper. When an unbalanced current from line to ground fault occurs, current will flow in the bonding jumper. When the current reaches the setting of the ground fault sensor, the shunt trip opens the circuit breaker, removing the load from the line. Another way a ground fault protector works is with a sensor installed around all of the circuit conductors. When current is flowing normally, the sum of all the currents is 0. However, a ground fault will cause an unbalance of the currents flowing in the individual conductors around the sensor. When this current reaches the setting of the ground fault sensor, a shunt trip opens the circuit breaker. When selecting panel boards and overcurrent protection devices, It's essential to know the available fault current for an application and the interrupting rating for the protected devices under consideration for use in the panel board. NEC Article 110.9 requires circuit protection equipment to have an interrupting rating sufficient for the circuit voltage and available current. There are two ways to achieve this requirement: full rating method and the series rating method. The full rating method requires all circuit protection devices to have an interrupting rating equal to or greater than the available fault current. For example, in the case of a building with 65,000 amps of fault current available at the service entrance, every circuit protection device must have an interrupting rating of 65,000 amps. This example is shown in the accompanying illustration. Note that the main circuit breaker and each branch breaker have an interrupting rating of 65,000 amps. Alternative to the full rating method is the series rating method, which requires that the main upstream circuit protection device must have an interrupting rating equal to or greater than the available fault current of the system, but subsequent downstream circuit protection devices connected in series can be rated at lower values. For example, a building with 42,000 amps of available fault current might have a breaker at the service entrance with an interrupting rating of 42,000 amps and additional downstream breakers rated at a lower level, but sufficient for the current that must be interrupted, 18,000 amps in this example. The series rating method is used when the selected series combination of circuit protection devices has been tested and certified by UL. Each series combination of circuit protection devices has a series connected short circuit rating. For additional information, refer to the series connected short circuit rating tables in the SpeedFacts catalog. Okay, so we've completed section 2 of the Basics of Panelboards. Let's begin the knowledge check. Question 1. Which of these items is part of a panel board interior? A. Access door. B. Bus bars. C. Trim. D. Dead front. Question 2. Which of these items is not a panel board main configuration? Is it A. Main switch. B. Main breaker. C. Main contactor, or D. Main lug only? Question 3. A 3-phase, 4-wire, delta-connected transformer secondary with 240 volts phase-to-phase and a B-phase high leg voltage of 208 volts has what voltage between A-phase and C-phase in neutral? Is it A. 120 volts, B. 208 volts, C. 240 volts, or D. 480 volts? The National Electric Code specifies that for each set of service entrance conductors, no more than blank switches or circuit breakers can be used to disconnect and isolate the service. Is the answer A. 3, B. 4, C. 5, or D. 6? Okay, last knowledge question in section 2. The blank rating method requires all circuit protection devices to have an interrupting rating equal to or greater than the available fault current. Is it A. series, B. parallel, C. full, or D. compound? Okay, now we're going to get into our final section before the final exam, and this part of Basics of Panelboards will cover the Siemens panel boards and its related accessories. Siemens P series of panel boards offers a stepped approach to power distribution. The P1 virtually eliminates common errors such as feed direction and main lug versus main breaker. Increasing distribution is simplified by the ability to add feed-through lugs. Because of its unique design, the P1 meets the majority of lighting panel needs. The highly flexible P2 provides options to fit most demanding specifications. Sized more like a lighting panel, the P3 packs the power of a distribution panel in a space savings, highly flexible design. The P4 is a mid-sized distribution panel that allows both fusible and circuit breaker branch and main devices. Finally, the powerful P5 allows larger fusible and circuit breaker branch and main devices and delivers the maximum power and flexibility to larger distribution systems. P-series panelboard interiors are designed to accommodate top or bottom feed. For 3-phase panels, the uppermost pole is always on A phase. the second pull down is always on B phase, and third pull down is always on C phase. As a standard configuration, branch breakers are mounted at the top of the panel with spaces at the bottom, regardless of the direction the panel is fed. All breakers except the plug-in type have bolted connections. The panel design provides bracing up to 200,000 amps, the UL short circuit rating. Keep in mind that this is not the interrupting rating of the panel, which depends on the circuit breaker configuration. Case-hardened, high-performance, thread rolling screws are used on the branch bus. P1, P2, and P3 panel boards are grouped together in this section because they are similar in construction and function. Like all P-series panel boards, these panels have symmetrical interior mounting studs and eliminate the problem of upside-down mounting. P1, P2, and P3 panel boards feature concealed fasteners and hinges with a flush door lock. P1, P2, and P3 panel boards are designed to be well mounted. The standard busing for P-series panel boards is temperature-rated aluminum with tin plating, but other busing options are available. P1 panel boards have the following features. Interiors have no top or bottom. To change from top feed to bottom feed, simply invert the interior. The dead front labeling is always right side up. Ratings from 125 through 400 amp for main lug panels and 100 through 400 amp for main breaker panels. They're field convertible from main lug to main breaker and vice versa with no increase in enclosure height. Feed-through panel versions include feed-through lugs, a sub-feed breaker, or a surge protection device. When feed-through space is not required, P1 non-feed-through panels reduce panel height by 6 inches. Neutral system is field upgradable to 200% capacity. Bonding provisions are shipped with each panel, suitable for use as service entrance equipment, assuming NEC compliance. 250 volt and 480Y 277 volt versions utilize identical boxes and fronts. The maximum number of circuits are 18, 30, 42, 54, or 66. The extended circuit options, the 54 or 66 circuits, often reduce project costs by elimination of the need for a second panel or the need to use a P2 or P3 panel instead of the P1. Authorized Siemens unassembled panel board distributors provide unassembled P1 panel boards that are high quality, labeled as suitable for use as service entrance equipment, and provide trouble-free operation. This program allows these distributors to provide same-day availability of unassembled panel boards that are an exact match with Siemens factory-assembled panels. Additionally, unassembled P1 panel boards have the following features to simplify assembly. The box is symmetrical, which means it may be mounted with either end up. The box is pre-punched for optional, field installable, door-in-door, or hinge-style trims. The interior is symmetrical, allowing it to rotate to change from top feed to bottom feed. Easy to use main breaker and main lug kits simplify the installation of mains. Branch neutral connections are near the breaker connections to speed wiring and reduce clutter. The panel has space to add a sub-feed breaker up to 250 amps, feed-through lugs, or a TPS-3 surge protection device kit. Siemens standard trim has hidden hinges and mounting hardware for added safety, and the panel door has a semi-flush lock as standard. P2 panel boards offer a wide variety of factory-assembled options to meet most lighting panel application requirements. The P2 design also offers the ability to mix breaker frames and unit space up to 225 amps to meet many power distribution panel requirements in a much smaller package. The standard busing for all P-series panel boards is temperature-rated, tin-plated aluminum. Various busing options are available and will be shown later in the course. P2 panels are available in 18, 30, 42, 54, 66, 78, and 90 circuit configurations. Blank unit space can also be added, if needed, to allow for future expansions or modifications. P3 panel boards are small footprint power distribution panel boards designed for use in applications that require more large branch devices than a lighting panel typically includes. P3 panels can include a wide variety of factory-assembled options and have the ability to mix and match breaker frames in unit space up to 225 amps. P3 panels are available with enclosure heights from 56 to 80 inches. Like other power distribution panels, P3 panel boards can include blank spaces to allow for future expansions or modifications. P4 and P5 power panel boards are similar in design and features, but vary in ratings available. P4 panels have a medium footprint to fit applications that require more or larger branch devices and higher current ratings than lighting panels can accommodate. P4 panel boards can incorporate circuit breaker frames and unit space up to 800 amps and fusible switches up to 200 amps. P5 panels have the largest footprint of any P-series panel, allowing even higher rated main and branch devices, including circuit breaker frames and unit space up to 1200 amp and fusible switches up to 1200 amps. There are 9 parts to the standard P-series panel catalog number. The first 3 parts are explained in the accompanying graphic. The remaining parts are explained on the next page. The accompanying graphic also shows a P-series panel board catalog number. The panel associated with the number shown has the following characteristics. Part 1 identifies the type of panel. This part number is for a P1 panel. Part 2 identifies the voltage system. This part number is for a 208 120 volt 3-phase 4-wire system. And Part 3 identifies the maximum number of circuits. In this example, that number is 42. Part 4 of the part number indicates whether the panel board has a main breaker, main lugs, or a main switch. For a main breaker panel, the 2-digit code identifies the circuit breaker. In this example, FX indicates that the panel board has an FXD6 main breaker. Part 5 indicates the panel board amperage rating. In this example, the panel board is rated for 250 amps. Part 6 indicates the bus material. The following table shows bus materials available. In this example, A indicates that the panel board has standard temperature rated aluminum bus bars with tin plating. Part 7 indicates whether feed location is from the top or bottom, and in this example, the panel board is top fed. Part 8 indicates whether the panel board is surface mounted or flush mounted, and in this example, it's surface mounted. And finally, Part 9 applies only to P1 panels. The N indicates that no feed-through space is provided. In this example, the T indicates that feed-through space is provided. Because less information is needed to specify a P1 unassembled panel board, a simpler 7-part catalog number is used. As shown in the accompanying graphic, Part 1 shows that this is a P1 panel, Part 2 shows that the voltage in the system, Part 3 shows the maximum number of circuits, Part 4 shows that the mains are convertible from main lug to main breaker, or vice versa. Part 5 shows the maximum continuous current rating or amperage rating. Part 6 shows the main bus material, and Part 7 shows that subfeed space is included. Note that the example provided is for a P1 unassembled panel board for use with a 208 120 volt 3-phase 4-wire system. It can accommodate up to 18 circuits, and it has a maximum continuous rating of 400 amps, and it has aluminum bus bars. You can minimize the potential for error by making sure that you have the correct answers to the following questions. What is the power system? Voltage, phase, number of wires? What's the interrupting rating required? Which NEMA type enclosure is required? How many circuits are required for a P1 or P2 panel? Or what will the enclosure height be for a P3, 4, or 5 panel? Does the panel board need to be suitable for service entrance? Suitable for use on service entrance labels are available, provided NEC requirements are met. What type of main will the panel board require? Main lug only, main breaker, or main switch? If the panel board will be a main breaker or main switch type, which main breaker or switch will be used? What amperage rating is required? What type of busing is required? Will the panel board be top or bottom fed? Will the panel board be surface mounted or flush mounted? Which branch device types and how many devices of each type are needed? Which accessories are needed? Any special mods? And when will the equipment be needed? Siemens coordination panel boards provide fusible solutions that make it simple and cost-effective to selectively coordinate a fused electrical distribution system. These panel boards are designed to address NEC selective coordination requirements. Selective coordination is a highly desirable design consideration for many businesses because selectively coordinated overcurrent protective devices help to avoid unnecessary blackouts that negatively affect business assets and productivity. Siemens coordination panels are especially designed for use in emergency systems, legally required standby systems, healthcare essential electrical systems, and critical operation power systems. Siemens selective coordination panel boards have the following ratings. Voltage ratings of 600 volt, 125 VDC, current ratings of 30, 60, 100, 200, 225, or 400 amps, main lug only, fuse main disconnect, or non-fuse main disconnect main options. They have up to 18, 30, or 42 branch circuit positions. You have neutral options of unbonded and bonded, 200, 400, or 800 amps. You have isolated or non-isolated grounds, a NEMA 1 or 3R enclosure, and the accompanying graphic shows the short circuit current ratings and also shows pictures of a panel and a branch disconnect with a plug-in CUBEF fuse. In addition to the P-Series and coordination panel boards described in the course, Siemens also offers C1 and C2 column type panel boards and telephone and equipment cabinets. The Siemens C1 and C2 panel boards have a narrow width suitable for column mounting. C1 panel boards are designed for 250 volt maximum supply, and C2 panel boards are designed for a 480-277 volt maximum supply. Both panels are designed for 250 amp mains and can be main breaker or main lug only. Siemens telephone and equipment cabinets are 5 3/4 inch deep, 20 inch or 24 inch wide, and vary in height from 23 to 59 inches. These cabinets feature Siemens FAS latch fronts with concealed hinges and fastening screws. For additional information about these additional panels and cabinets or other products described in the course, refer to the SpeedFacts catalog, which is available online. Accessories add to the performance of a panel board or adapt the panel board for specific application requirements. Various accessories are available for Siemens panel boards. The remaining pages of this course provide a few examples of those accessories. Again, refer to the SpeedFacts catalog for a complete listing. Some accessories modify the circuit breaker. For example, it's sometimes necessary to trip a breaker from a remote location. This capability might be required for a variety of reasons, such as when it's necessary to have a panic button that de-energizes machinery for safety reasons. One way to accomplish this is to provide power to the machinery through a circuit breaker equipped with a shunt trip accessory. The shunt trip may be part of the main breaker, which will shut off the entire panel board or part of the branch breaker. The shunt trip device consists of a coil in series with a limit switch. When the circuit breaker contacts are closed, the limit switch is closed. Depressing a customer-supplied push button energizes the shunt trip coil, causing the breaker's mechanical latch to disengage the trip mechanism and opening the circuit breaker's contacts. When the circuit breaker's contacts open, the limit switch also opens, which removes power from the shunt trip coil. After the breaker has been tripped, it must be reset manually to reapply power. Torque, Sangamo, or Paragon time clocks are available as an accessory for P-Series panel boards. Time clocks are available with 1-pole or 2-pole, single or double throw contacts, or 3-pole single throw contacts. They are rated for a maximum of 277 volts. A time clock can be used to turn control of a branch circuit or an entire panel board. The accompanying illustration, for example, shows a time clock connected to a panel board that controls the outside lights for a small commercial building. This allows the lights to be turned on and off automatically at specific times. When an application requires remote control switching of loads, an ASCO 911 or 920 mechanically held remote control switch or Siemens LEN electrically held contactor can be mounted in a separate cabinet as a main disconnect. Many electrical devices and systems are susceptible to damage from the high energy levels associated with electrical surges caused by lightning or other electrical equipment. Any component between the source of the surge and ground can be damaged. Therefore, electrical systems are at risk unless they incorporate surge protection. Surge protection is best accomplished by stopping surges before they get in through the application of hardwired surge protection devices, which are installed at key electrical system surge entry points. Siemens TPS-3 surge protection devices are designed to the UL 1449 3rd edition standard for hardwired SPDs, or surge protection devices. TPS-3 SPDs provide the highest degree of safety while delivering some of the industry's best performance ratings. Siemens TPS-3 family of commercial SPDs share common performance parameters and are offered in two configurations. Integral SPDs, these are designed into our equipment, or an external or wall-mounted SPDs. TPS-3 options are available for Siemens panel boards and other distribution equipment. One example of an integral TPS-3 SPD is a P1 panel board option that bolts directly to the panel board bus bars. Once installed, LEDs indicate that the device is working and provide voltage and diagnostic monitoring. There is an audible alarm and test button. Options include a surge counter and a remote monitoring device. Okay, time for the last knowledge check before the final exam. Question 1. Siemens P1 panel boards can be converted from main lug to main breaker panels in the field. Is it A, true, or B, false? Question 2. Standard busing for P-Series panel boards is temperature rated blank with blank plating. A, copper silver, B, copper tin, C, aluminum tin, or D, aluminum copper. Question 3. P5 panel boards can accommodate circuit breaker frames in unit space up to blank and fusible switches up to blank. Is it A, 800 to 200, B, 800 amp and 800 amp, C, 1000 amp and 1000 amp, or D, 1200 amp and 1200 amp? Question 4. Which option allows a user remote from a panel board to remove power from all of panel board's branch circuits? Is it A, shunt trip accessory on the main breaker, B, shunt trip accessory on a branch breaker, C, a TPS-3 system, or is it D, none of the above? Okay, question 5. Which panel board option reduces the potential for damage from electrical surges? Is it A, a shunt trip accessory, B, a TPS-3 surge protection device, C, remote control switch, or is it D, lighting contactor? Alright, time for the final exam. You must score an 85% or better to pass. Here's question 1. Which of the following statements does not agree with the NEC definition of a panel board? Is it A, used to control light, heat, or power circuits, B, placed in a cabinet or cutout box, C, mounted in or against the wall, or D, accessible from the front or rear? Question 2. Panel boards are covered by NEC Article A, 376, B, 402, C, 408, or D, 424. Question 3. Which of these fuse classes has the lowest interrupting rating? A, H, B, J, C, L, D, T. Question 4. The item used in a Siemens panel board to cover unused pole spaces is called A, dead front, B, QF3 filler plate, C, trim, or D, label. Question 5. A NEMA-type blank enclosure is intended for outdoor use, primarily to provide a degree of protection against rain, sleet, and damage from external ice formation. Is it A, 1, B, 3R, C, 4X, or D, 12? Question 6. Panel board working space dimensions are provided in NEC Article. Is it A, 110.26, B, 230.71, C, 240, or D, 408.16? Question 7. Which of the following is not a common type of panel board main configuration? Is it A, main breaker, B, main switch, C, main contactor, or D, main lug only? Question 8. On a 3-phase, 4-wire, weak connected transformer, with a secondary voltage of 40 volts phase to phase, the phase to neutral voltage is blank volts. Is it A 120, B 240, C 277, or D 480? Question 9. On a 3-phase, 4-wire, delta-connected transformer with a B-phase, high leg, and a phase-to-phase voltage of 240 volts, the high leg voltage is blank volts. Is it A 120, B 208, C 240, D 480? Question 10. According to the NEC, the maximum number of switches or circuit breakers required to disconnect and isolate the service from all other equipment on service entrance equipment is blank. Is it A 2, B 4, C 6, D 8? Question 11. The neutral conductor is blank grounded at the service entrance panel board. Is that A, always, B, never, C, rarely, D, often? Question 12. The neutral conductor is blank grounded at panel boards downstream from the service entrance panel board. A, always, B, never, C, rarely, D, often. Question 13. NEC Article 230.95 requires ground fault protection of equipment for solidly grounded weed electrical services of more than 150 volts to ground, but not exceeding 600 volts for each service disconnecting means rated blank amps or more. Is it A 100, B 250, C 1000, or D 2500? Question 14. The blank rating method requires selection of all circuit protection devices with interrupting ratings equal to or greater than the available fault current. Is it A, individual, B, group, C, series, or D, full? Question 15. Blank panel boards are designed to be fully convertible from main lug only to main breaker and vice versa. Is it A, all P series, B, P1, P2, or P3, C, P1, or D, P2? Question 16. Blank panel boards are designed to accommodate fusible switches. Is it A, all P series, B, P1s, P2s, P3s, C, only P5, or D, P4 and P5? Question 17. Position 3 in the part number of P2 panel board indicates the blank. Is it A, number of circuits, B, height in inches, C, width in inches, or D, current rating? Question 18. Which of the following is not a busing option for P-series panel boards? Is it A, silver-plated aluminum, B, silver-plated copper, C, 750 square inch aluminum, or D, 1000 amp square inch copper? Question 19. A blank is an accessory used to trip a circuit breaker remotely. Is it A, remote control switch, B, shunt trip, C, time clock, or D, contactor? And finally, question 20. Siemens blank option is used to reduce the potential for damage to sensitive equipment resulting from electrical surges. Is it A, LCP, B, C1, C, TPS3, or D, LEN? Well, that concludes the Siemens Quick Step Basics of Panelboards course. I'd like to thank you for your time and attention in learning the material. We appreciate the business. Thanks again.